Now this is the tale of a girl who lived in a faraway land. She dreamed of being a star, was dealt the cards not in her hand. She never let it get her down, see, she had a plan. She would build a rocket and get up off of that rock, call home full of crabs and clams. Man, all she ever wanted was to shed a little bit of light and shine, but not in a blink.
Hello everyone, so thank you for tuning in to this Cast from the Classroom Lunchtime session. And my name is Alex Codoreanu, so thank you for sticking around with our original technical difficulties. And hello. I am a PhD student here at Swinburne University within the Center for Astrophysics and Supercomputing. And I'm also a Castro student, which stands for the Center of Excellence for All-Sky Astrophysics. I'm in my last year, and my research here has focused on understanding how much stuff there is between and around galaxies. What I mean by that stuff is just what we commonly refer to as metals or baryons, or just the building particles of what we consider to be matter. In order to do my project, I had to use a spectrograph on the Very Large Telescope, which is in Chile, and that's its actual name. It has a single mirror that is about 8 meters across. I'm close to 2 meters is what I tell people, so it's about 4 of me end to end that would be able to fit across the entire mirror. Now, actually getting the data is just the first step. We have to use, like for example, I had to use a supercomputer here at Swinburne, so it's a Center for Astrophysics and Supercomputing. So we had to do that not only just to really reduce the data, meaning that we're counting how many photons are being trapped by this telescope at a particular wavelength, but then we also had to really carefully consider the statistics implied by the observations. So in order to do this, we had one set of observations, and then I created thousands and thousands and thousands of different observations based on those parameters in order to just really understand how much confidence we can have within the statistics that of our discovery. Specifically, what I do is, like I said, I analyze light, and I analyze light that is emitted by quasars in order to identify the clouds and galaxies that this light passes through. Just to give you a bit of an idea, quasars are a bit of the, I guess you'd call them cosmological lighthouses, meaning that they're very, very, very bright, so we can see them from very, very far away. The photons that we collected a few years ago for my PhD were actually emitted when the universe was just 1 billion years old. So as you can imagine, these photons have seen quite a bit. The universe now is about 13.8 billion years. So they've traveled for a very long time just to be trapped in a telescope in Chile. So given these really large scales, what I'm going to focus in today's talk is just try to connect very small scales of atomic physics to the large scales of cosmology. So how is it that a little photon can tell us so much information about the stars and the galaxies? So first things first, let's just remind ourselves how big the universe is. So I'm going to switch to my computer, and here we go. All right, so as you can see, we start around our planet, and this is where the photons have to arrive. So we have some sort of telescope somewhere, and then if you zoom out, you can see that we're starting to see sort of the scale of what we call the solar system. Well, and compared to a drive to Perth, this is a very, very, very long way across. So we're getting to about a few light days across, meaning that it takes light a few days to cross this distance. As we step outside from our planet and we move through the solar system, we realize that our sun, which is a star, is just one of billions in our galaxy, which is about 120,000 light years across. That's a very long distance. And there are billions and billions of stars within this galaxy. Now, this galaxy, as large as it is, compared to our scale, is just one of just billions of galaxies in itself. These billions of galaxies themselves form along large-scale structures called cosmological streams. And you can see as that you start looking farther and farther distances, these structures themselves become apparent. And as we step back even further into time, we see that there is this mosaic, if you will, of the early universe. This entire story, it's commonly referred to as the bell of cosmology. You can kind of see it. This is a very common picture that you you'd be able to see. So you can see that there's the Big Bang, inflation, first stars, dark energy, and so now. This entire story really, the story of light within the universe as we understand it and the light that we can capture really starts about 380,000 years after the Big Bang. At this point, the universe is dominated by photons, and there are loose protons and electrons around that are being knocked apart by photons. As the universe, though, expands, it cools down, and it gives an opportunity for these hydrogen and helium atoms to start forming, meaning that protons can capture electrons and create simple hydrogen. Now, this time of the universe is called the Dark Ages, and the first stars are starting to sort of pop on and turn on into existence. Now, as these first stars form, they explode, they go supernova, and they throw even more metals, and they pollute the universe, and the first sort of galaxies form, and these galaxies continue to grow, merge, and evolve, and create the picture of the universe that we sort of have today. And somewhere along the way, the solar system also forms, right? So the solar system itself is formed about 5 billion years ago, and this is a timeline of what the formation of the solar system. So we have the star turning on, and as you can start seeing, there are planetoids which are starting to are gravitationally bound to the star and are starting to circle around, clearing the neighborhood, thus beginning to form the definition of what a planet is. And as the star itself blows away some of the dust, it gets to the current picture that we see today. Now, if we wait a couple more billion years, our sun becomes a red giant and expands all the way out to Mars. So we have to figure out how to not be around when that happens. A few billion years later on, this red giant will become a white dwarf. And if we look in the universe, we can see that there are white dwarfs. So this is an incredibly beautiful picture of a dwarf. So you can see the white spot of light. That is the star that is left behind. Now, what makes this really interesting is that little pinpoint of light is about has the mass of the sun, but it's only about the size of the Earth. So it's incredibly compact. So far I've just sort of presented a few movies and talked a bit about some of the pretty pictures and some of the big narratives. But let's focus in on some more specifics, right? So our sun is a star, which the definition is that it's a collection of gas whose gravitational collapse is supported by nuclear processes, meaning that as stuff is trying to go towards the center, something happened called a nuclear process, and that stops gravity from collapsing. Well, what is a nuclear process? One of the processes that is incredibly important in this story is called nuclear fusion. And that simply means that you have two atomic nuclei, they join together and they form a new, heavier nucleus. But the mass is just a little off, so usually there's a release of energy, and we'll talk a bit more about this. One of the most basic, or rather the first nuclear fusion process that we can talk about is called the proton-proton chain. Now, in this particular chain of reactions, there are two pairs of hydrogen atoms that bond to create deuterium. Now, this further binds with another hydrogen atom and creates a helium-3 atom. Now, as more and more helium-3 atoms are created, they fuse with each other and create a helium-4 and an extra 2 hydrogen atoms. Now, there are billions and billions of these reactions happening in our sun every second. And these reactions create a result of, you get 2 neutrinos, 2 gamma rays, and a little bit of energy. So we start with 4 hydrogen atoms and end up with a helium-4 atom. So that's the beginning and the end product. And, what's really important is to understand what's inside. How do we know this stuff, right? So by actually looking at the neutrino flux, we can measure how many of these reactions are happening. And by looking at the spectrum of the corona, we can read the chemical patterns of the sun and get its chemical composition. So, as you see, we have more than 98% of this fuel. So we're safe. Our sun is going to be around for a bit. But how do we get the rest of the material? So you can see that if we trace the evolution of hydrogen and helium, which are these primordial elements, and trace how they become other elements, we can trace the history of the universe. And to really understand this, it's a very simple concept. you can only use the fuel you have, right? So if you only have hydrogen and helium, that's the only fuel you have. How can you create something else? Well, as more and more proton chain reactions happen, the ratio of helium to hydrogen changes. And as the ratio of helium to hydrogen changes, some of that helium can bond to itself and become a carbon. Now, as the carbon, as the sort of the first carbon elements happen within these stars, they start to also interact with the hydrogen, which is also present. So you can go through this carbon, nuclear, nitrogen, and oxygen cycle, the CNO cycle, and you can turn 4 protons into 1 alpha particle, 2 positrons, and 2 electron neutrinos, and again, some of that very famous energy. Now, these nuclear fission processes can only really continue to iron 56. What that's called in astronomy is called the heavy iron peak. And in order to really understand that, here I have a plot of the average binding energy per nucleon as on the y-axis, and on the x-axis is the number of nucleons in the nucleus. So basically, what we have is how many protons and neutrons make a nucleus, and the energy required to separate the nucleus members or to unite them. And if you notice, at the where I drew that blue line, that's where iron 56 is. So if you notice, as you go from 0 to 56 or so nucleons, the average binding energy increases, and then as you go past the iron, the average binding energy decreases. What that means is that in order to get any of those heavier elements, you have to take in additional energy, while as you create lighter elements than iron 56, you're releasing that additional energy. This additional energy that I've spoken about a few times already is mass loss, meaning that as I get 2 hydrogen atoms and create 1 helium atom, and as I take 4 hydrogen atoms and create 1 helium-4 atom, if I add up the actual mass of my input versus the output, is just slightly off. But as you can see, like a very small change in mass, that m in the E equals mc squared, is actually translated into a large amount of energy because you're multiplying by the speed of light squared, which is an incredibly large number. So this mass loss that we keep talking about it basically follows that pattern. And this extra additional energy which is needed comes in the form of gravitational collapse, meaning that as we start producing more and more iron, the gravitational collapse is pushing these atoms closer and closer together, and it creates a supernova effect. Now, if we say this, that we have supernovas and stars are forming, some of the questions that we need to answer is, where do stars form? How do they form? And are all stars the same? I bet you already know that not all stars are the same, but where do they form and how do they form? Well, in order to answer these questions, we needed to basically use the Hubble Space Telescope. Now, to give you an idea of the size of the telescope, that's the astronaut right there, and that is the camera. It's about 2.4 meters across. So I'll just let you think about that particular. It's an incredibly large telescope. Now, what you can do with a telescope like this is you can take incredibly detailed pictures of the universe. Here's one of the Eagle Nebula, and you can see it's kind of dusty and there's a lot of stars forming around there. Another famous one is the Omega Centauri globular cluster. Now, if you look at the globular cluster, there are red and blue and yellow stars. So what we can do is we can separate them by color, right? And when we separate them by color, we can then start thinking about doing some statistics. One of those statistical tools is called the HR diagram. Now, the HR diagram, like most plots, will have 2 axes. And I am just told that the slides are not really in focus, so let's just try this. Now, the HR diagram has an X and Y axis, And on the y-axis, it's the magnitude, how bright the object is. If we say absolute magnitude, that refers to how bright the object is intrinsically. And on the x-axis, we have temperature. And at this point, we have a telescope, so how do we get temperature? There's no thermometer on the Hubble Space Telescope. So in order to get the temperature, we use something called, we fit it to a black body curve. So those beautiful pictures that we took of the globular cluster itself, it actually is formed of a few different pictures. So we take just the red bit, just the green bit, just the yellow bit. And when we put that together, we can create something called a black body. We can then find which black body curve best fits that color pattern. So you can see blue stars have larger surface temperatures than yellow stars, which are themselves brighter at the surface than red stars. I bet you can guess that our sun is a yellow star, so the surface temperature is about 6,000 degrees. Now, just to kind of give you an idea of how this works, when we plot when we put the stars on the diagram, the hot and bright stars will be in the top left corner, and they generally tend to be more massive, and they don't live as long. Colder and older stars are on the bottom right, and they're less massive, and they tend to live the longest. So our sun happens to be, if you've been keeping track of the axes, happens to be just about in the center, and it's on what it's called the main sequence. Now, the main sequence is the distribution of stars as the star family is born, right? So as the stars are born, they all sort of fit into this distribution. And as we saw with the sun, as our star will evolve, it'll become a red giant, and then it'll become a white dwarf. So by looking where the stars lie on the HR diagram, we can actually get the age of a stellar population. So that's already really cool, because we can just simply take a picture and just look at the color and be able to identify how old that stellar population is. But even and we're not done, just with this one graph, we can also discover something else. Now, I said that this is the absolute magnitude, meaning how bright the object is. So meaning that if we are, 1 light year away from the sun, we know exactly how much energy we expect to get from there. But when we look at the night sky, they all sort of seem to be the same color. So how can we tell how bright, what the temperature is? Well, to really understand this, it's incredibly, it's exactly the same physics as understanding how hot a fire feels, right? So if you're staying really close to a campfire, you'll feel that it's obviously warm, but then if you step back, it'll feel colder. So by figuring out this difference between how hot the fire should be versus how hot the fire feels, we can actually get the distance. So with stars, we know how bright they are, we measure how bright they appear, and that tells us how far away they are. So the HR diagram is an incredibly useful tool in telling us how old and how far away a star is. But I hope you've noticed that it actually depends on understanding the evolution of a single star. So it's by understanding how the nuclear fusion processes work, which makes this particular science possible, really. Now, as supernovas go off, they throw metals into the interstellar medium, and the shockwave itself can also trigger further star formation. So what I mean by that is that as a supernova goes off, that pressure can spark further star formation. And again, the shockwave then jumpstarts the creation of a new star in another dusty and gaseous region of the universe. And the process begins again. Now, because stars themselves start in these dusty, nebulous regions, there's plenty of material for new planetoids to form, which then again clear their neighborhoods. As the star matures, it blows out the leftover dust, and we have another solar system. Now, to give you an idea of how many times we think this cycle has repeated, our sun is a third generation star. But because we discovered it first, we call it a population 1 star. As we started looking towards the center of the galaxy, we figure out that there are even older stars, and we call those population 2 stars. And the first stars, which formed only from hydrogen and helium without having the benefit of a supernova event helping them along the way, we call those population 3 stars. So just today, we learned that using simple statistical tools and understanding nuclear physics and having access to incredible facilities like the Hubble Space Telescope and the Very Large Telescope in Chile, we've learned how to take our knowledge of nuclear physics, figure out how stars are formed, and use that, and understanding how they go supernova, and use that in order to understand the evolution of all metals throughout the universe. Now, these supernovas spread metals, and in astronomy, when we talk about metals, we're just saying it's not hydrogen or helium. And this triggers further star formation in nearby clusters. Now, understanding how these very small scales and these very small sizes, understanding the physics on these very small sizes, really leads to an understanding of the large scale of the universe and the cosmology. And this is an incredible, incredible thing. Now, of course, this is something that it's only possible in the last 20 to 30 to 40 years. If we're to have this discussion 100 years ago, what we think of the universe when we talk about cosmology would be just our galaxy. But it's the advent of these new facilities, really, and our ability to have better and better computers that has led us to an understanding of how truly vast the universe is. But even with these large scales, it is our understanding of how the universe works on these very small atomic scales that have let us understand the larger things at work. So thank you very much, and I look forward to your questions. Thank you. Hello. I should be getting some text, I believe, from Jeanette. If you want to put up the, you can ask on the live chat as well. So we have our first question about seeing differences in star color. So with the star color, what we actually see, we have incredibly narrow bandwidth. So if you were a participant in one of the earlier talks in the week, there was a discussion on spectroscopy and wavelength. So light comes in all wavelengths. And what happens is if we select just a very small portion of that spectrum, we call that color. And by creating narrow bandwidths and selecting several of them, we can look at the difference, and that's what we call color in this particular sense. So, especially with the globular cluster diagram, we can identify very accurately what the color is. Now, when we say color, obviously it doesn't refer to what it looks like to the eye, but rather the physical mathematical difference between the integrated light at those particular wavelengths. Thank you for the question, though, Carl. That was a really good one. That we can't. Oh, so with the naked eye, we can only see. So the question is there the potential for stars to exist that we can't see with the naked eye because of their wavelength? So we can only see a very small percentage of the stars within our own galaxy. So with the naked eye, we definitely cannot see any stars in different galaxies. What happens though is these galaxies that we can't see, it isn't because of their wavelength per se, but rather because they're very, very, very far away. So, for example, going back to my campfire analogy, if somebody's having a campfire in Perth, you're not going to get any warmth from it here in Melbourne. Thank you, Carl. So the question is, what is the maximum distance that we can see? So with our naked eye, oh, thank you, with the naked eye. I think you've stumped me there. I would say maybe, so a few light years we can definitely see. Maybe like 10 to 15 light years, perhaps. But when we think about whatever that radius might be, it's an incredibly small, very small part of the galaxy itself. So not very far at all on cosmological scales. Very far away if you're thinking just of like normal distance scales. And let me know if that answers your question. Great. We promise. So thank you very much for joining into the Castro in the Classroom live stream today. And feel free to send me any other questions that you might have if you think of any later on. Oh, there we go. Hey, Luke. So as you saw, 98% of our sun is still made of hydrogen and helium. When we're looking at the metallicity, it's just the ratio of other metals to hydrogen. As you can tell, it's already pretty small. So we talk in logarithmic scales when we talk about these metallicities. So it's not a very large amount, but it's a consistently a large amount, difference in logarithmic scales. So a population 1 star, like ours, which is a 3rd generation star, which gets a little bit confusing. Was confusing for me when I first learned it. So the first stars, what we call population 3 stars, in the early universe were 100% made of hydrogen and helium. There's some very light traces of lithium, if you go back to some Big Bang cosmology stuff, but for the most part, very close to 100% hydrogen and helium. So it's very small differences, but these small differences on these very large scales are quite significant. So it's not so much the amount of stuff, but the fact that this little bit of non-hydrogen and helium elements have been able to make it across and pollute these further generation of stars is what makes it different. I agree. It is very interesting. I'll later on a bit more. If you have any more questions, I'll be right here. All right, everyone. So thank you for participating, and see you next year. Bye.
Now this is the tale of a girl who lived in a faraway land. She dreamed of being a star, was dealt the cards not in her hand. She never let it get her down, see, she had a plan. She would build a